All right, good afternoon, ladies and gentlemen. Good evening. Welcome to another series of tutorials with me, Aubrey. In this lesson, we are in the time series section. Now, before we go on, if you've not subscribed to the channel already, please subscribe. The subscribe button is red if you've not subscribed, and it is gray if you have subscribed, right? So please subscribe, leave a like, and comment. Now, in this lesson, we are in the time series section, and we are looking at a very interesting question here. The question reads, derive the autocorrelation rho k for some k equals to 0 all the way to infinity, and show that the autocorrelation function of a stationary zero mean of a number one process is given by, so this is the equation of a number one process, and we asked to show that run is equal to this. So there are basically two questions here. So the first question is derive the autocorrelation rho k, which is basically to show this right here, right? Show that. So in this lesson, I'm going to do the derivation of the autocorrelation as part of this lesson. Then in the next lesson, we are going to derive the rho 1 autocorrelation. We're going to show this. So it will be in two parts, so watch out. So this one, we're deriving rho k. In the next part, we're showing this right here. All right, so let's get started. Right, see, so by definition, the autocorrelation is defined as, so autocorrelation is just equal to the expectation of xt times xt minus k. So that is the kth autocorrelation is defined by this. For some k equals to 0, 1, or on. All right, so basically how we're going to derive this is by analysis. So by analysis, we're going to test for k equals to 0. So say by analysis. So if k equals to 0, k equals to 1, k equals to 2. So by analysis, we're going to check what rho k is for some k equals to 0, k equals to 1, and k equals to 2. And from these three sequences, we can define the nth or the kth sequence. All right, so that's what we're going to do. So we start for k equals to 0. We're going to have, let me just put it right here. So for k equals to 0, we're going to have rho 0, which will be equal to, we put in the expectation there, so that will be the expectation of xt times xt minus 0, since the k is 0, so that will be xt minus 0, so that will be just xt, okay, which is just equal to the expectation of xt squared. Now, what is the expectation of xt squared? This is just variance. That is at least for stationary 0. So how does this come about? So variance of let's say some variable y, okay, assuming that y is a stationary 0 or is a constant, has a constant variance, just like we were told here that for stationary 0. So we're assuming that the mean of the white noise is 0. So for some variable y, the variance of y is the expectation of y squared minus the mean of y. That is just y. So now the mean of y, which is a white noise, is just equal to 0. So if the mean of y is 0, then what we're going to get is that the variance of y is just equal to the expectation of y squared. So same thing that is happening here for xt. So variance of xt is equal to the expectation of xt squared minus the mean squared. Now the mean is constant for et and xt. So this is what you should remember for the rest of the video, that for et and xt, the mean is equal to 0 since et is a white noise, which has 0 mean and variance. And we're assuming that the mean is constant and the variance is constant. So the mean is 0. So meaning that the variance of xt will be equal to the expectation of xt squared. So wherever we see something squared, expectation of something squared, we'll just take that to be the variance. So remember this, wherever we see expectation of something squared, we'll take that to be the variance. So at least for time series, when we have a stationary mean that is 0, all right? So for row 1, we've checked the box. For row 0, sorry. Row 0 is just equals to 1 times the variance. All right, so this is equation 1. Now we check for row 1. All right, so remember row k is equal to the expectation, okay, to the expectation of xt times xt minus k. So for row 1, this would be equal to the expectation of xt t minus 1. All right, so again, this is just, we know that xt being an ARMA on one process has the equation xt minus 1, that's the error term, plus beta et minus 1. Okay, so meaning that row 1 would just be the expectation of xt, which is this. So I can just drag this here. So is that which is our xt times our xt minus 1, xt minus 1. Okay, so we distribute that. We have row 1 being equal to the expectation of, so this times that will be a xt minus 1 squared, right? Then I can distribute the expectation, or let me just take it step by step. Plus et, expectation of t minus 1, plus beta et minus 1, then xt minus 1, right? So now you can distribute the expectation, but a few things that you need to remember about expectations is that when you have expectation of x times y, this is just equal to the expectation of x times the expectation of y. When you have the expectation of ax, this is, we can factor out the constant a, expectation of x. So that is what you need to put in mind, even as we'll be distributing the expectations. So yeah, so start distributing. So row 1 will just be equal to the expectation, or we can factor out the alpha. So it would be this expectation of this, but we factor out the alpha, so it will be alpha expectation of xt minus 1 squared. Here we say expectation of et times expectation of et. So it will be expectation of, sorry, et times expectation of xt minus 1 plus, same thing here, we factor out the beta, expectation of et minus 1 times expectation of xt minus 1. All right. Now, since et is a white noise, basically et is a white noise, so it has mean 0 despite having a variance. So so this would be 0 and this would be 0, so making these parts 0, and we remain with row 1 being equal to a expectation of xt minus 1 squared, right? So this is 0 because of et expectation, which is just the mean of et minus 1 lag away, just be 0. So we're going to have that, so meaning that row 1 is just equal to a times the variance. Remember what we said about the expectation of something squared is just the variance. All right, so far we've had row 0 being equal to 1 times the variance. We've had row 1 equals to a to the power 1 times the variance. Okay. This can just be written as a to the power 0 times the variance, because it will give us the same. A to the power 0 is just 1. Yeah, so now let's check out row 2 so that we see how the pattern progresses. So for row 2, so for k equals to 2, we know that row k is equal to the expectation of xt times xt minus k. So for k equals to 2, we're going to have the expectation of xt times xt minus 2. Now remember, our xt is an ARMA 1, which is alpha xt minus 1 plus the error term plus beta beta et minus 1, right? So yeah, so replacing our xt in row 2, we're going to have row 2 being equal to the expectation of, so we replace our xt in the equation, literally replacing. So replace for xt, replace for xt in xt times xt minus 2. Okay, what we're going to have for row 2 is the expectation of, so we can start distributing. So we say this times that will be a xt minus 1. Now how I'm going to write xt minus 2, that xt minus 2 can be written as xt minus 1 minus 1. So that is how this can be written. So I'm going to write for xt minus 2, I'll write it like that. So we start distributing. So we have xt minus 2, which is just this, times that, it will be times xt minus 1 plus et times xt minus 2, which is just that again. So it will be xt minus 1 plus beta et minus 1, then times xt minus 1, right? So yeah, so basically we distribute the expectation, or we can let yeah, let's distribute the expectation. So row 2 would just be equal to the expectation of axt minus 1 times xt minus 1 minus 1 plus the expectation of et, just like we were distributing before, times the expectation of xt minus 1 minus 1 plus beta expectation of et minus 1 times expectation of um, xt minus 1 minus 1, right? So basically here, we see that expectation of VT, just like before, this is 0 and that is 0, so this will be 0. So what we're going to remember with for row 2 is just alpha expectation of xt, alpha xt minus 1 times xt minus 1 minus 1. So we're going to change the variable for t minus 1. So we'll let t minus 1 be some variable s, so that it looks more clean. So so row 2 will just be a expectation of xs for t minus 1 times, this would be t minus 1 would be s xs minus 1. So we have that, where sx, again, where sx s is just an ARMA 1 with that, an ARMA 1 with that equation, s minus 1 plus es, again, plus beta es minus 1. So that is that. So now see that row 2, you can replace xs, which is this equation, replacing this equation for xs. We see that we have replace it here, replace it, then we multiply it by xs minus 1. Again, we see that row 2 will just be equal to a. Then we distribute just like we were doing. So we distribute throughout, then we distribute the expectation. We're going to have expectation of a. So this times that will be xs minus 1 squared plus this times the expectation, that will be expectation of es times expectation of xs minus 1 plus beta expectation of, remember this is, the alpha is distributing everything, so but we're not distributing it yet. So times expectation of des minus 1 times expectation of xs minus 1, right? So just like before, expectation of this is 0 and that is 0, so this will be 0. What we're going to remain with is row 2 being equal to a expectation of a xs minus 1 squared. We factor out a, so we have row 2 equals to a squared expectation of xs minus 1 squared. Now remember, the expectation of something squared, so you can write it out here so that you can get more. It's just that. So remember, the expectation of something squared is just equal to the variance. So this is a squared times the variance. All right. So now we look at the trend. So row 0 was equal to, row 0 was equal to a to the power 0 times the variance. Row 1 was equal to a to the power 1 times the variance. Row 2 was equal to a to the power 2 times the variance. We see that the trend continues. So for row k, this will be equal to a to the power k times the variance. Okay, that is for row k. And if we want to write this more nicely, we can write this in terms of row um, row row 1. So we can say row k is equal to a to the power k minus 1 times a. So that these are same bases. When the powers add, we're going to go back to k. So times the variance. So this is just row 1. This is row 1 here. So we see that row k is equal to a to the k minus 1 times row 1. All right. For k equals to 2, because we don't want to start at 0. We're going to have a negative exponent. We want to start at 2 so that we have 1 and so on. So for k goes to 2, 3, 4, and so on and so forth. So yeah, so basically that concludes our proof. See you in the next lesson.